Right, so we want to finish this part on the 2D systems, and just as a quick refresher on what we've seen, I'll just go through that. So we looked at the convolution and looked at the proper equation of doing that. So that's a delta function, and we said that okay, convolution is derived from the linear shift invariant systems. So linear shift invariant system is just the extension of the linear time invariant systems we had in 1D. And so the only difference here is that now you can translate the picture, like the results after translation should stay intact. And we say that the kind of operation that fulfill that linear types of operations, and that's in particular for that's convolution. Okay, so we talked about this is the equation for the convolution, and all I said is basically you take every single pixel in a picture and you do a weighted combination of your neighboring pixels. Now the equation here is a bit messy because of this inversion here, but that's just because so that the maths are similar to what you've seen with 1D, and you shouldn't worry about that too much. So we said that the number of properties that are interesting with convolution. So if you convolve an image with a mask, so the mask will be defined by this matrix of weights, then you can commute them, so you can say that it's same as the convolution of the mask by the image, or you have associativity and distributivity as well. Okay? So all very nice properties, and sometimes you don't think about them too much, but actually turn out to be quite useful. Right, so we finished last time, I think, by saying that basically you have to be careful with the considerations of computational considerations. So you have to look at every single pixel, so you have to do that, and you have to look at a small window defined by your mask. Okay, so if your mask is say 11 by 11 pixels of size, that means you're going to be looking at 121 neighboring values. Means for every single pixel in the image, you have to do 121 multiply add type operations. Okay, and that turns out to be quite a lot when you do that for the 3 channels. You end up quickly with a few giga operations per second. Okay, and so even standard hardware starts to become a bit of an issue. And even when you look at most modern computers and so on, they struggle with video. Okay, so usually the effects you can do on videos are very light effects. You can apply a little filter, you can apply some few things, but they're quite slow. And when you look at what's going on in deep learning, even the operations you do in deep learning, they're just a bunch of convolutions put back to back. This becomes impractical for real-time playback. Okay, so people use deep learning. They use that mainly for frames, not really for 24 frames per second types of operation. Anyway, very quickly, all this becomes an issue, and usually it all boils down to not so much the number of operations you have to do, but the amount of data you have to pull. Okay, something I won't go too much in detail here, but just be aware. Usually, the main culprit for a slow performance is memory. Okay, pictures are big. To get all that kind of data around you, it takes a bit of time. If you look at a picture which is 4K, so you have 4,000 pixels, and if you're looking at 11 by 11 block, means you're going to have to pull 11 lines from your image, and that's 11 times 4K pixels. Okay, so already just to find the results of the computation of your particular pixel, you see that you need to read in your memory something like 50 or 60,000 pixels just to be able to read what these 11 lines are doing. So you need to have them fetched and put closer to you. and then from these 11 lines of your picture, you need to extract the part of interest. And anyway, so to process any pixel, you need to have really gathered 11,000 pixels from your 60,000 pixels from the picture. That's quite a lot. Okay, so memory and bandwidth and how you access memory is usually the main problem here. Right. So something you will see, I think it's in the next lab. It's something which is quite useful. It's sometimes you can. All right. So first and foremost, usually the types of operations you do, they're usually 3x3 or 5x5 filters. Okay, you don't use big mask. You usually use small mask for precisely that reason, that it's slow. The second trick here we can do. Okay, so instead of just working with big mask and small masks, what we can do is to use these separable filters. Okay. So separable filters means are types of filters that you can basically obtain as a cascade of two 1D filters. So this is how it works, okay? There's a bit of maths, but it's just because it's easier to actually write down the equations and to work out what's going on here. So on the top left, so that's the output of the particular pixel of interest. And here, what you have is the standard straight equation from a convolution. Okay, so I is the picture you're looking at, and P is the mask where all the weights are stored. So you see, you sum over all the pixel locations, so indexed by N1 and N2. So use that sum of basically all the coordinates in your picture. And you say, well, you're going to add that particular pixel location, and what you need to look at is the weight that relates that location to my current position. Okay, so he only refers to from the distance from the relative distance between the pixel N1, N2, and the pixel HK. So you have two pixels, one is position HK, and the other one is position N1, N2, and you say they're far apart or not, okay? But the weight that relates, the relative distance is stored into P. So that's your convolution. Now, if you can express, so separable filters are filters where you can say that the actual value of your mask here is really just the product of two functions. One that's only looking at the first coordinate, so say y, and the second coordinate, so x. All right, so we say the mask here, there's some kind of symmetry, which means that to know the value of this this part of the mask, I only need to multiply. It only depends on what's going on in the x and the y separately. I don't need to know. There's no kind of joint behavior. Okay, it's kind of a, you have to do two things separately. If you do that, then you can reorganize the computation, and you can basically write down the equations as two 1D convolutions. Okay, so you can say I first do a convolution of my picture with just a simple 1D vector, and then followed by another 1D. So here's an example. Okay, so this is your 2D matrix. Okay, so it's a typical blur matrix. I mentioned a few of those. Basically, if you have positive numbers everywhere, usually it's a blur. Okay, so if you do a weighted sum of your neighbors, kind of regardless of how they're positioned, you end up with the visual effect is for you it will look blurred. Okay. So we say that this matrix, 2D matrix, can be obtained as the product of pointwise element of these two matrices here. Okay, so one is 1D, so 1, 2, 1, and the other one is 1D, but on the vertical axis, and 1, 2, 1. All right, and because here 4 is 2 times 2. Okay. So because of this kind of symmetry, horizontal vertical symmetry of this matrix, it means that instead of doing the convolution with a 3 by 3 mask, I can organize my computation by saying I'm first going to convolve my picture with this simple, simpler mask, and then follow that by this other mask. Okay, so you have 2 stages now. So you replace one big convolution, which is 2D, by 2 1D convolutions back to back. All right. I'll show you an example of that, and that will be in the lab as well. So here's the reason why it's interesting. Okay, now we do 2 convolutions, and why would that be more simple? Well, it's simpler because these 1D convolutions are much simpler. Okay, so this is the full equation. So your picture is of size n by m, and R and C are the size of your original mask. And because it's a 2D mask, then the number of pixels you have is R by C. So this is what you get. And on the denominator here is the number of operations you do for doing things back to back. And basically, the first operation is, so you convolve the picture, so still n by m, but this time the size of the kernel is only, on the mask, is only R by 1, so it's really R, okay? But because you have this second stage, you need to do plus C. And you can see very quickly why it's interesting, because now you have a ratio of R, basically it's R squared divided by R, okay? If R and C are the same, then you have something R squared divided by 2R, so you have, so you save quite a lot there, okay? And very quickly, your computations are much faster. Right. So the last point, I think, of this slide is about causality. So remember, in 1D signals, okay, we probably talked a lot at length about causality and non-causal filters and so on. And the discussion here will be a bit faster because it's a bit, there is no notion of order in a 2D signals as such. Okay, so in a 1D signal, you can order things. You can say, this is the past, this is the future. And here it's a bit, it's not really quite clear what's going on, okay? But still, we can extend that to 2D, and I'll show you some examples, okay? Now, everything is in the slides, so you have to read that in more detail in the slides. So a non-causal system, it means like it's a filter that requires for you to know the future, okay? And a causal filter means you only need to know the past, okay? So what you can do is you can define what the past and the future is in the picture by saying maybe the pixels on the left are the past and the pixels on the right are the future, and the pixels on the top of the image are the past and the picture on the bottom are the future, okay? So you can do this kind of stuff, and that's kind of a typical way of thinking about it. So if you look at the causal filter here, you see looking at this particular pixel, and so if you process the picture from the top left to the bottom right, so kind of typical ordering, so you will go as a kind of skyline order. So you start here, and then you move on to the next pixels and so on, and then you move on to the next line, and then so on and so forth, okay? So if you have to process this particular pixel, which are marked in orange here, but you need this pixel to compute the output of that one, then it's still causal because you would have seen all these values will have been seen before, okay? Because you traversed the picture from here to here, so when you reach that point, you would have seen all these pixels before, so therefore it's causal. And similarly here, this is clearly non-causal because to process this pixel, I need to have information left, right, bottom, top, so I need to know the future, so therefore it's non-causal. And there is this thing called semi-causal, which is like, it's causal in one direction, but not in the other. Okay, so in this one, for instance, it's causal because you only need to know the past in the y direction, but here you need to know a bit of the future. It's a technical point, okay, it's just kind of the going back on the, here we're just trying to see what works, doesn't work from extending from 1D to 2D, okay? So obviously, causal and semi-causal are not that much of an issue to think about too much in 2D because there is no such a thing as past, really. Last point is all the operations we have seen here. So we introduced the convolution as being a special symbol and special type of operation. But all that could still be it's just part of just all the linear operations you can do on a picture. And to understand that, like the most generic way of thinking about that is to say, okay, forget that a picture is a matrix. Okay, so this. You say I have a picture, I call it I for image. And I say, well, this is the 3x3, it's a 3x3 picture, and these are the values of my pixels. That is fine. But we could try to reorganize all these points and just say it's a vector. Okay, so in Matlab, we'll just call we'll flatten the vector, the matrix, and we get basically a vector. And now we say, let's assume that my picture is a vector. Okay, so I just stack all these pixels. I cannot lose the spatial natural organization of the picture I will see it. But we just reorganize that and say it's a vector. And we call it small I. Okay, and now most operations I've talked about. Okay, so well, all of them can be expressed into simple linear algebra. So you say the kernel. The convolution by the mask is actually a matrix operation, and we can call it matrix H. And if we do H times I, so I is my picture now, I get a new picture G that is actually represent the output of the convolution itself. Okay, because all what I've done so far is just doing linear algebra. I've done like weighted sums of my inputs. So really, this is all the same. All right, so here is an example of this, okay? That looks pretty horrible. So this is the mask. This is a 3x3 mask. And we had that before, but basically, sorry, maybe this one. Yeah, this would be this non-causal mask, okay? So -1 everywhere, and you have a 4 here, okay? So it's a simple edge detection filter. Basically, you compare the local pixel with the average of the neighborhood, okay? That's what it does. So if you're in a flat region, there's no difference between your pixel and the neighbors. But if there's a difference between this pixel and the neighbors, I mean, you have some texture, so that will have non-zero values. So that particular system could be written in this way. So once again, my picture is of size 3x3. I only have 9 pixels. And all the values of these pixels are expressed in that column vector here on the right. And what you have here is this convolution operation being applied. Okay, so I know that the result of a particular filter or for a particular pixel, I just have to apply this vector here times this vector. Every time you have a 0 means that the pixels are not neighbors, so therefore you don't want to take them into account in the computations. Right? So it's a very sparse matrix. I mean, basically, if the picture is bigger, you have only zeros everywhere almost, except on these diagonals. Okay. It's not necessarily a trivial thing to represent in your head, but basically, think of it this way. When you do convolution, it's a solution of for linear system, okay? And everything in the word linear, okay? So linear system means you have a linear equation somewhere, and you end up with linear algebra, okay? So there's no surprise here. It's all the same type of things. All right, and the reason why this is useful is because this is the most generic way of doing things, and there's a lot of research and really cool stuff happening, trying to do inversions of these matrices and so on to be able to get really cool effect. I'm trying to find you some examples of that in future lectures. But yeah, you can start to do matrix algebra, and you can do inversions of matrices and so on. All right, so yeah, deconvolution is one example of that. So for instance, so deconvolution is a classic example, okay? So let's say you blur your picture, all right? So you know the operation for the blurring, okay? You know you've done some study, you study the system, you say, right, it's a blur of this type, and therefore I can derive what H is, okay, what the mask of that particular blur is. So you say, okay, I have access to, so I don't know if you remember Hubble, okay, so when Hubble was launched into space, they had an issue with the optics, and all the pictures were kind of blurred to some extent, right, and a bit of a disaster. So they had to go back and fix the lens. But for a while, what they were doing is they were deblurring the pictures in software. Okay? And deblurring the picture in software is as simple like you can do it now, all right, to some extent. So we know what the blur operation is. The blur operation is a convolution. Okay? So you apply this blur kernel, you apply it to the picture, and you get a blurred picture. Now, what we want to do is the inverse operation. How do you remove that blur operation? And now you can see with the matrix representation, this is just a matrix inversion. Okay, so we say G is our blurred image. H, we have some estimate about that, what the blur function is. What we're interested in is in I. Okay, so you can say no, trying to find the unblurred picture that, once you apply the blur, will give you back the blurred picture, right? So you could say I is H minus 1 times G, okay? So something like so, okay? And that's the inverse problem, trying to find what the undistorted image is. And then you realize, okay, now, if I think that, if you had only convolution, that would be kind of hard to think of how you go about doing that. But now you're like, okay, right, so it's just matrix algebra, I can apply that. Right. Obviously, this is not something we do usually, okay? We rarely do that because the matrices are huge, okay? I mean, here you have maybe 4 million pixels in your picture, and if you have now a matrix, it'll be 4 million by 4 million entries, which is a bit big. Right, so these were examples of blur, and I was just going to show you maybe how we get that into Matlab to maybe show you some examples of that. All right, so let's see, what do I have here? All right, picture of a bird. So what I'm going to do is close this guy, make a bit of space. All right, so we're going to work in grayscale because working in color just means you have to think all the time that you have 3 channels and so on. Let's just work in grayscale and have this sorted. So this is my picture in grayscale, and I'm going to convert it to double because between 0 and 1, okay? Right, so now it all works out, okay? I'm going to define a mask, a convolution mask. So let's call it H, and what I'm going to do is I'm going to put a lot of ones. And so if I look at that, I have 19 values of 1, okay? And I'm going to normalize that by 19 so that the average, I can get an average, okay? So I'm just going to say H divided by 19, and now all that sums to 1, okay? Right, so the operation for the convolution in Matlab is conv2, and sorry, I'm just going to look at, show you the help for there. So it takes your two images, so A and B, perform the 2D convolution of your matrices, and now there's an order, okay? So if you convolve A by B or B by A, and then you can say what kind of, how do you want to output your picture, okay? So if you do same, it means that you're going to preserve the size of your picture, okay? The picture doesn't change. If you have valid, it will only compute the convolution for the pixels where it can find a valid point in the previous image. So that means that if you're close to the edge, like if you're at the border of the picture, then you can't get the result of the convolution because you need to access probably points that are outside of the boundary. So therefore you don't do it. So if you apply valid, then it will shrink a bit. If you do full, he will compute the output for all the pixels that might have, that might require a valid pixel as an input, which means that the output picture will actually be bigger than what you set it with. So anyway, let's start and let's see what it gives us. Okay, so we're going to convolve the picture Y with this, and I'm going to use same. All right, so if I do look at what this picture looks like, this is what we get. So okay, so you can see there's it's blurred. Okay, so let's say like every time you apply convolution with only a positive mass, it's blurred, and it's quite clear. Okay, so it's a horizontal blur, and that's because every single so the entry I get, it was a horizontal matrix only with ones, so there's nothing happening on the y-axis, but now you start to average 19 pixels across at every single time, and this is what you get. So okay, small details. Okay, so very important ones. The picture dips to black on the edge of the picture, and that's because here we assume that the extrapolation, so when we pick the pixels that are outside of the range of the, okay, so to compute this pixel, I need to have access to pixels that are on the right, okay, and they're not defined, so by default we assume that the value is 0 in this case, all right. So that's why it dips to black, because now you're mixing with black values. Of course, when you're on top and bottom, you don't have that effect because you don't have any vertical blur. You can do, so if you do valid, for instance, okay, then it's kind of hard to see, but it's not obvious. How to put it. Yeah. If you do valid, okay, you can look at just the size of G, and you see now the size of Y. You can see the height is the same, but the width, which is always the second coordinate here, is actually smaller. Okay, so we went from 443 to 425. Okay, so valid means you shrink because there's things you cannot compute, and if you go for the full, it gets extended, but you can see it dips even further to black, okay? Because to compute this pixel, I only had a reference of only one pixel that was valid in the other picture, and all the other one was incorrect. All right, so let's do more. So that's classic blur. You can do as well, a classic one would be 1 minus 1, for instance. Or I could do it this way. So basically here I'm going to take the, depends where you put the center, but I mean the current pixel minus the previous pixel, okay? All right, so here the picture is black, mostly, but you can see some parts that are not that black, okay? And that's because basically the value, I'm just going to look at two consecutive values. Usually the values of the pixels, nearby pixels, are very similar. So most of the time it's going to be black, so 0. And sometimes it's going to be negative, which won't be shown here. And sometimes positive, in which case you'll see a tiny bit of something going on here. You probably want to, if you're doing a different filter like that, to be able to see what's going on, you probably need to rescale that. And so I'm going to rescale it by offset it by at least 0.5. So now everything which is 0 would be gray, and everything which is brighter than gray. So mid-gray means there is nothing, there's no difference. And bright, like white colors, means there is a big positive difference, and very dark color means there is a very negative difference. I'm just going to scale a bit down the effect, okay, and maybe just have something like that. All right, so this is, you can see how this could be used as an edge detection mechanism. Okay, so if you want to find the edges in your picture, applying this kind of operations, reveals all these edges, and here we're going to reveal all the horizontal, we're processing the picture along the horizontal axis, so we will reveal the vertical structures. So basically, if you have a horizontal line, okay, so something which is fairly horizontal, it won't show up too much. But if you have something very vertical in your picture, because you process the picture along the horizontal axis, you're going to hit that vertical structure, and that's going to show up very nicely. I can do the same with, I'll just show you what the, let's give them names, okay? Let's call it IX, and let's call it IY, and I'm going to put a transpose operator here. Well, I could put that. This. I'm going to put a vertical mask. Okay, so now I'm going to compute the difference along the vertical axis, and I can show you what so this is along the x-axis and along the y-axis. All right, so if you look, for instance, here, this is not the best picture for showing that, but this kind of, okay, if you look at the feather here, this is a vertical structure, okay, vertical line, and by applying here what's the horizontal filter, you pick up the edge boundary very nicely. Okay, so it's very dark, and so it's very clear. But if you apply a vertical difference, pixel difference on this vertical structure, then the edge boundary is not that clear. All right. We'll have another exercise at some point with medical imaging, trying to find histograms of orientations of fibers and stuff like that. But basically, here's already a convolution does this kind of stuff. Okay, so you can get blurry pictures, or you can get difference of you can pick up edges and so on. All right. So that's it for convolution. I wanted to finish as well on histogram equalization, and we'll continue with that particular picture. Okay, so let's come back to showing what the original picture is. So this is our current picture, and I'm going to quickly show you what the histogram for that picture is. So it's called H, so the histogram of all the values we have in the picture between 0 and well, it's still going to look for 255 values, but there has to be scale between 0 and 1. And all right, so this is the histogram of that particular picture. So the histogram tells us, if you look at, so now I'm working between 0 and 255, okay? If you're looking at a value of 100, then you have 3,000 pixels that are this way. Now, let's try to work more in terms of the cumulative probabilities we talked about. Okay, so first going to look at the number of elements in your picture, and that is basically the width times the height of my picture. Okay, so that's the number of pixels I have in my picture, and now I can divide my histogram by the number of pixels. So now I have a representation here in terms of frequency. Okay, so here I know I have 1% basically of the pixels that are of that particular color. All right, and so that's one thing. So the other thing is I'm going to look at the cumulative sum. So let's call it F, and Matlab has a nice function for that, which is called CumSum. And basically what it does is going to look at the cumulative sum of all that. And now, if you look at this, this is what you get. So what this tells you is, like, if you read a value at, so for a particular pixel intensity, so 100 here, you read something like, say, all right, so say 0.4, okay? That means that you have 40% of the pixels in this picture that are that have a color which is less than 100. All right, make sense? And so if you have, if you look at 255, then you see that you have 100% of the pixels in that picture that are less than 100. Now let's see the effect of applying a color transformation, okay? And I'll probably just end up there. So I have my picture, and I'm going to modify it slightly. And I'm going to say that, I don't know, I'm going to change the, I'm going to decrease the contrast, okay? All right, so now the picture, I've reduced the contrast by half. So the picture is a bit kind of more, yeah, has this less tones, okay? So you have more, less contrast. You know what, I made a mistake here, should be +5. All right, be more visible, okay? So this is the original, and this is after color transformation. So, similar story, so I can compute what the histogram for that picture is. And I can plot okay, so now you can see the histogram is more compressed. Right? So actually we reduced by half the range of the histogram. And interestingly, if you look at the cumulative histogram, oh, sorry. So these are the two ones we talked about, okay? So you can see that things have changed, okay? So it's more compressed as well. But what is the most important part here is that there's something that hasn't changed, okay? So if you look at the value 100 in our original, we say we had 40% of the picture, which is less than 100. But now if we apply the same transformation to 100, so we say it's, so try to find that transformation here. So 100 corresponds to this value. So that's the same transformation I applied. So now the new value is, mapped 100 to 113 basically. And if you look at 113 in the new version, it'll be here, and you get exactly 40%. Okay, so you know exactly that that the transformation hasn't changed the proportions. Okay, I mean the threshold is still intact, so there's still the same proportion of the pixels that are less than that. Okay, I don't really have time to show you exactly how we do histogram equalization from here, but that would be in the, I won't cover that anymore in lecture, but that would be in the files I will give you. That will just give you the last steps on how you go from here to histogram equalization. Okay. All right. That's it.